Okay, to get going with momentum, of course, you can look up the lessons in the PDF notes and in YouTube, but the basic idea is this. Momentum is a variable we abbreviate with the letter P. I'm not sure why. Maybe the word momentum has a silent P like the word pneumatic, but in the word momentum, it's also invisible. And to calculate momentum, you take mass times velocity of that object. And one of the reasons we like momentum is because it makes sense to talk about the total momentum of a few objects, which is just the momentum of object 1 plus the momentum of object 2 plus ... for however many objects you have. Now, why do we talk about momentum? Well, because the change in momentum, which is called impulse, Star Trek fans may remember something about impulse engines, is equal to the integral of force through time. And often we end up using delta P is equal to the average force times delta T. So if you replace the force with its own average value, then it's a constant and it comes outside the integral, then you just get the integral of dt, which is just delta T. So that's one aspect of momentum when you're talking about a single object. When you're talking about multiple objects, the reason we like total momentum is that we have this Newton's third law, F12 equals F21. And that means that delta P2, that is the change in momentum of object 2, is minus delta P1. And that's because of this relationship over here for each individual object. If you integrate the force through time for object 2 and then do it again for object 1 on the other side of the equation, you get the change in momentum of the corresponding object. And that means that delta P1 plus delta P2, both vectors, is equal to 0, which means P1 plus P2 is equal to some constant. So during a process in which the only significant force is the force two objects exert on each other, which is equal and opposite by Newton's third law, there should be a minus sign here somewhere. I'll put the minus sign on that side. Because those forces are opposite to each other, the corresponding changes in momentum are opposite to each other. So the change in total momentum is 0, which means that the total momentum itself is a constant. So let's do an example momentum in 2D. So I want to figure out spherical asteroid with a radius of, say, 500 meters, so it's a kilometer across, is moving at, let's say it's moving at 20,000 meters per second. What's a good speed for an asteroid? Yeah, that's a reasonable speed, according to my impact event search. So the first thing we could do is we could calculate the momentum of this asteroid. So let's assume that the density is rho equals, let's go with 8,000 kilograms per meter cubed, which corresponds to iron and steel. So then the mass is rho v is 8,000 kilograms per meter cubed times the volume of a sphere. The volume of a sphere is 4/3 pi times the radius cubed. So I can dig out my calculator here. But probably the last thing that was heard was that I was just typing this into Google and I found I had a mass of 4 times 10 to the 12th kilograms. So now when I want to calculate the momentum, I take the mass times the velocity. So that is my 4 times 10 to the 12th kilograms times 20,000 meters per second. So I just take all that stuff that I already had there times 20,000 is a heck of a lot of momentum. 8 times 10 to the 16th kilogram meter per second. So let's say that this asteroid was heading for Earth. And I have a rocket engine that can produce 2 million newtons of thrust. And I wanted to stop this asteroid using this rocket. So then I can figure out how much time it takes to stop this asteroid with delta P equals force average delta T. And if you're just going from motion to stopped, then you're talking about a one-dimensional problem. So our delta P is going to be minus 8 times 10 to the 16. And then our average thrust is going to be minus 2 million newtons. And of course, we'll make our thrust negative because we want to slow the thing down. And we get delta T is equal to that number over 2e6 for 2 million, which goes back to 4 times 10 to the 10th. Yeah. Seconds. And let me get that back up here. So if I divide that by 3,600, then I get the amount of hours, and it's still a big number that I don't understand. So I'll divide it by 24 hours, and I get 484,000 days. So I'll divide that by 365.25, and I'll get 1,327 years. That does not seem feasible. Yeah, Earth would have a problem. Maybe we only have 3 months of lead time on the project. And let's assume we have 1 month of thrust. What if we exert the thrust sideways instead of exerting it in reverse? So now I need a diagram to symbolize what's going on here. Here's our mass with its V initial. And it is heading for the nice green planet Earth. Ah, first of all, I want to circle. Second of all, I'm going to draw in my circle some uh, some approximation of what I think Earth looks like. We got some stuff up there. We got stuff up there. We got stuff up there. There. That's my impression of Earth. You're supposed to say how nice that looks. So down here we have the deflected path with an angle theta. So I want to find this angle, and in order to find the angle, my adjacent side is 20,000 meters per second times 1 month. So that's basic constant velocity kinematics, 20,000 meters per second times 1 month. And Google does the unit conversions for me, and I get 53 million kilometers, which is 53. Yeah, let's just use million kilometers times 10 to the 6 kilometers. So that's the adjacent side to my theta. The opposite side to my theta is our Earth. That's not some chemistry like ideal gas constant or something like that. Um, that is the radius of Earth. Oops. So that is 5378. Oh, it's 63, 6,400 kilometers. So that means that my tangent theta is equal to 6,400 over 53 times 10 to the 6th. But we also have a graph that we can draw where we have our V initial over here, and then our V final is going to be like this. And this right here, that's delta V. I drew my V final in the wrong spot. So here's delta V, and here's V final. So if we can get the velocity of this asteroid to go from a straight across in this diagram velocity to slightly tilted downwards, then we will have caused the path to veer away from Earth. And as it turns out, our tan theta is the same angle in this diagram. Tan theta is delta V over V initial. So then I can set up a relationship that says 6,400 over 53 times 10 to the sixth is equal to delta V over 20,000. So then my required delta V is 6,400 times 20,000 over 53 E6 is 2.4 meters per second. And that's the magnitude of delta V, I guess. Now, why do I care about that? Because if P is equal to mv, then delta P is equal to delta V. This is just a subtraction of two m times v values, and you can factor the m out of both of them, and you just get m times delta V. So this is my mass of my asteroid, which was 4 times 10 to the 12th. Kilograms times 2.4 meters per second. So times 4e12 is 10 times 10 to the 12th. Kilogram meters per second. It's like 9.6 or 9.7. And now I can use my delta P is equal to F average delta T. So delta T is delta P over F average is 10 times 10 to the 12th. And what was my rocket strength? 2 million newtons. 2 times 10 to the 6th is 5 times 10 to the 6th seconds. Now, I don't know if that's good or not. Let's divide that by 3,600. That's 1388 hours. I still don't quite know if that's good or not. Is 58 days. Okay, so that's still not good. This is a terrible example. I just destroyed the world. So that tells me we better catch this more than 1 month ahead of time. I don't think you need to go quite out to 2 months, because if you go out to 2 months in this calculation, then the angle's going to be smaller. Then it would only take 30 days. So I think if you increase the amount of time by the square root of 2, then the required angle will decrease by a factor of the square root of 2, and we will meet what the required time and the actual available time will meet and we will successfully catch the asteroid. But definitely, we better catch this asteroid more than 1 month ahead of time.